Good morning, class. We are looking at exam 2 review. Basically, it's going to cover chapter 3 from section 3.1 to 3.8, differentiation rules. So, we are going to cover derivatives of polynomials and exponential functions, the product and quotient rules, derivatives of trig functions, the chain rule, implicit differentiation, derivatives of the logarithmic functions, the rates of change in the natural and social sciences, exponential growth and decay, and then a couple of sections left in the next exam, related rates, linear approximation, and differentials, hyperbolic functions. So the definition, dy dx is the limit of delta y over delta x as delta x approaches 0, or f prime of x is the limit of f of x plus h minus f of x over h as h approaches 0. This is the definition that was used previously. And with the help of the following, the limit of sine theta over theta as theta approaches 0 equals 1, the limit of cosine theta minus 1 over theta as theta approaches 0 equals 0, we got other formulas. For example, the derivative of x is 1. If you are differentiating c times f of x, you can take the c out, and the derivative of the sum is the sum of the derivatives. The derivative of the difference is the difference of derivatives. E is defined such that it's either the limit of 1 plus 1 over n to the power of n as n approaches infinity. And right away, by the way, you can write this in different formats. For example, if you let 1 over n be h, this becomes h, this becomes 1 over h, and it goes to 0. Or the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. These are some stuff that we've come across in this chapter. And it gives rise to the following formulas. Constant, the derivative is 0. X to the power of n is n, x to the power of n minus 1. Sine is cosine, cosine is negative. Sine, tan is secant squared, cotangent is negative cosecant squared. Secant is secant x tan x, cosecant x is minus cosecant x cotangent x. So this is a bunch of formulas we need to be comfortable with, but I wanted to give you the synopsis in the beginning. Then we have the product rule, and this is a shorthand notation. It's a quotient rule. If you've learned it differently, that's fine. But when you write it in this fashion, f prime g plus g prime f, then it makes it easier to memorize the quotient formula of f prime g minus g prime f over g squared. And there are more formulas, the composite function and the chain rule, more formulas such as extended power rule, exponential formats, logs, inverse trig functions. So we have a ton of formulas, and this is the synopsis of the whole thing. And it is important to get comfortable with those, because when we go to the reverse process, anti-differentiation or integration, it is a must. And we are going to practice with all of those. Let's start with a very simple example, and that covers what's known as the basic rule of differentiation, which is the power rule. The derivative of x to the power of n is n x to the power of n minus 1. Therefore, if I'm differentiating x to the power of 1,000, 1,000 becomes the coefficient. And let's just write this actually with steps so it becomes clear. Therefore, y prime, 1,000 becomes the coefficient, and the exponent goes down by 1 according to this formula. Therefore, the answer is 1,000 x to the power of 999. y equals 3r squared. It works in the same manner. So this one remains, and then r squared, we follow the power rule. So 2 times r to the power of -1. What I want to add here is the notation. dy dr, ddr, which is the differentiation operation of 3r squared, is 6r. 3 times 2, 6r. And what is extremely important is to understand the following. When we write dy dr, we are telling the reader what is the independent variable. See, I can write y prime here, I can write y prime here, and they are absolutely fine. But in this case, if I want to go with this notation, which is the Leibniz's notation, dy dr, over here I would write dy dx. So the notation for here would be dy dx, telling the reader the independent variable is x. Now, what if we have a bunch of terms? So we have a polynomial, and we are going to differentiate term by term. X to the power of 8. Again, we are using the power rule. 8, x to the power of 7 plus 12 remains. You're going to multiply it by 5. 12 times 5, 60, x to the power of 4 minus 4 times 4, 16x cubed plus 10 times 3, 30x squared minus 6, and a constant results in 0. And that is extremely important to pay attention to, that we have various formulas and we should be comfortable with. Again, this is 8, this is 12 times 5, which makes it 60. 5 goes down to 4. We're going to multiply -4 by 4, gives us -16. 4 goes down to 3. 10 times 3 is 30. 3 goes down to 2. Minus 6x is simply -6. And 5 gives you 0, which we don't write. We're going to move on. We are going to differentiate this. And again, just to refresh your memory, I have the formulas. For example, the derivative of constant is 0. The derivative of k times x is k. The derivative of x to the power of n is n. X to the power of n minus 1. Some of the formulas, just to refresh everyone's memory in the beginning, and ultimately with practice you memorize. So in order to do this, first and foremost, square root of x must be changed to x to the power of 1/2. We are going to distribute the x, and remember the exponent for x is 1. 1 and 1/2, they add up to 3/2. So it becomes x to the power of 3/2 plus 5x minus 2. To differentiate this, 3/2 becomes the coefficient, and it goes down by 1. So this becomes 3/2 x to the power of 1/2. 3/2 minus 1. 3/2 x to the power of 1/2. And this gives us 5. This goes away, becomes 0. And since it was given in this format, we put this back into the format of a square root. 3/2 square root of x plus 5. What is extremely important for everybody to see, as far as I'm concerned, is the following. This is the only calculus step. Algebra, algebra, algebra. So we don't have too many calculus steps. Here's the next one. F of x is 2x to the power of 5 over 9x to the power of 9. To differentiate this, we're going to put it in the format such that we can use the power rule. So 5 and 9, 5 minus 9 makes this 2 over 9x to the power of -4. So that's an algebraic step. Then we are going to find the derivative. Y prime is 2 over 9. Going to multiply it by -4, and then x to the power of -4 minus 1, or x to the power of -5. And this is -8 over 9, x to the power of -5. -5 goes down, and it becomes x to the power of +5. What is the derivative of pi squared? Anyone? What would be the answer here? What do you think?
2 pi.
Is it, class? What is the derivative of pi squared? What is the derivative of 10? What is the derivative of 1/2? What is the derivative of 10 billion? What is the derivative of E? Any constant, the answer is 0. So I want you to be very careful with that concept. Because it's pi squared doesn't mean it's 2 pi. Pi is a number. Therefore, the answer is simply 0. We want to go with the product rule. And as I mentioned in the beginning, if you look at what I have here, fg prime is f prime g plus g prime f. Of course, we have the details in the lecture section, but this is a shorthand notation. F stands for f of x, g stands for g of x. If we multiply two functions, how do we differentiate them? Is f prime g plus g prime f, and I can't emphasize the importance of this shorthand notation, at least as far as I'm concerned, because it makes this one easy to remember. So if I want to multiply these two, and this is a warm-up example, we are not going to simplify. The purpose is just to apply this, and I want to mention again that there are not many calculus steps. There's only one simple calculus step. Of course, there are a few algebraic steps to finish it. You can finish it at home later on, but for now, again, you're going to memorize the formulas, and then when you're doing this, you can write the formula and follow that. So if I call this the f of x and this one the g of x, then I need, according to the formula, f prime, which is 4x cubed minus 6x squared, and this gives us 0. That's f prime times g. Just write the g next to it, plus g prime, 6x minus 5, that's g prime, and just write the f next to it, times that, And of course, it needs simplification, but that's not what we are concerned with now. I highly recommend you do that later on. But for now, I want you to see the importance of your only calculus step, f prime g plus g prime f. And of course, it has to be distributed. This has to be distributed. You have to combine them, so on and so forth. So that's an example you didn't have to simplify. But let's look at this one. I put a raised dot in between, indicating we are dealing with a product rule. So if you call this the f function, this is the g function, then according to the formula, I need f prime, which is 2x times just g sine x, plus I need g prime, the derivative of sine, which is cosine x times x squared. So let's write at top of it f prime g plus g prime f. If you follow the formula, it's a lot easier than keep on writing d dx of this, d dx of that. You don't want to do that. So the only change we are going to make, basically, we're going to write this, and this one we put it in front because we don't want anyone to be under the assumption this is x cubed, because it's not. You put the x squared in front, and that's your final answer. Another warm-up example, and this time for the quotient rule. And again, f prime g minus g prime f over g squared. If you call the numerator the f of x function and the bottom g of x, or simply g, we're going to follow this. So we have a huge fraction bar, f prime. So we need the derivative of the top. We've seen this expression before. It's 4x cubed minus 6x. You simply multiply it by g, by the denominator, just put it next to it. And then minus sign, g prime. The derivative here So we have f prime g minus g prime. Well, the derivative of g is 6x minus 5. And then we're going to put next to it f, the top function, the numerator. And then the bottom, simply you write this in a parentheses and square it. That's all you have to do. Again, this requires simplification. This is the only calculus step, and you need to take a couple more steps to finish the job. But the purpose of this to show you just how to apply the very first step, which is a calculus step. So this is the only calculus step for this quotient rule. The next thing I want to look at this example, and it is extremely important to know when to use the quotient rule and when not to. Okay. Anytime you have to use the quotient rule, if you try to avoid it, you probably make a mistake. And if you don't have to, it's easier to see the easy way out using your algebraic techniques, and don't use that. We can have two fractions. The first one is 10. The second one is minus 7x. And clearly the answer is minus 7. The point is, am I trying to avoid the quotient rule? No. If I have to use the quotient rule, I must. So if we can divide, if the denominator has one term, and sometimes it's not necessarily a term, it's an algebraic expression. For example, if it's square root of x, you can still do the same thing. If the numerator is a number, you can do the same thing. You don't have to use the quotient rule, but sometimes we must. All right. The limit of sine 3x times sine 5x over x squared. As x approaches 0, we want to find it. And reminding everybody that sine, the limit of sine theta over theta as theta approaches 0 is 1. The limit of cosine theta minus 1 over theta as theta approaches 0 is 0. So what can we do? Well, notice that we have 3x and x squared at the bottom, 5x and x squared at the bottom. And also notice if the argument of sine, in this case theta, is identical to the denominator, the answer is 1. So for example, this one, if we had sine 3x over 3x, we would get 1. This one, if we had sine 5x over 5x, we would get 1. So the very first thing we do, we can separate the x squared into x and x. Then we notice that if we had number 3, we would be in good shape here. If we had number 5, we would be in good shape here. So if we throw in number 3, in other words, we can multiply the top and the bottom both by number 3. That's fine. The fraction is being multiplied by 3. Same thing we can do here. We can multiply the top and the bottom by the same number. In this case, we need 5. So we're going to multiply it by 5. And so this piece, you can think of this as theta. You can think of this as theta, and the 3 can come out. And the same thing here. You can think of this as theta, this one as theta, and this can come out. Now, what is extremely important is the following. So let me show you. You want to make sure that this one, and this one are the same. Since x goes to 0, so does 3x. And they're all identical. Since x goes to 0, so does 5x. And notice they're all 5x. Now, you can change this if you want, for example, to 3 for this one. You can change it to 3, the limit of sine theta over theta as theta approaches to 0. Or you can leave it, that's fine. And we can write the second one as 5, the limit of, let's say, sine alpha over alpha as alpha approaches 0. If we write it like this, that means we let alpha be 5x. And over here, we let theta represent 3x. But even if you don't do that, then you should recognize, since this one, and this one are identical, this is 1, so 3 times 1, this is 5 times 1, and the answer is 50. And that's fine with me if you want to skip that step. But it is important to know, if it's x, you have to change this to 3x, because this one, and this one must be identical according to this identity, if you will, according to this limit. If you want to use that one, then the 3, the argument of sine, the denominator, and this piece that is approaching 0, they must be identical for it to work. For part B, we don't know the answer the way it's given, but since we have those, we can divide the top and the bottom by theta. And by the way, theta is not 0, theta is approaching 0, otherwise you can't. And this piece now looks like this one. This piece looks like this one. So we can apply the limit to the top, apply the limit to the bottom. The top becomes 0, the bottom becomes 1. The final answer is 0. So the key is, if you're using this, make sure the argument of sine, the denominator, and this variable are identical. All right. the limit of cosecant x times sine of sine x as x approaches 0. We want to find this. Well, again, we see it's perhaps similar to this. Somehow we can use that. This is sine of sine x. So this cosecant x, as you know, it's 1 over sine x. That's the reciprocal identity. That's equal to 1 over sine x. Let's use that. So what you're looking at here is that if you let sine x be theta, okay, you can replace this as theta, you can replace this as theta, and you can replace this as theta also. Why is that? Why is that? Because if when x goes to 0, also sine x goes to 0. That's why, in essence, this is like sine x. You can do that. So I want to make sure everybody understands that they are all identical, meaning we are looking for this one, and this one to be the same. This and this are the same, but this is not. Since x goes to 0, sine x goes to 0. Therefore, we can replace everything with theta, and obviously the answer is 1. What about the limit of sine x squared over x as x approaches 0? Again, maybe we can somehow use this. The argument is theta, the argument is x squared, so the denominator should have x squared, and it doesn't. Because you can't change the argument. It's extremely important to see that there's nothing you can do here. So how do we change this to x squared? We can multiply this fraction. We can multiply the top and the bottom by x. So it creates x squared in the denominator. So you can see that you can put this whole thing together. So it's the limit of x as x approaches 0, and the limit of sine x squared over x squared as x approaches 0. But remember what's going to happen here. So we are separating them. When x goes to 0, so does x squared. You have to change it. Why am I changing it? Because now the argument of sine, the denominator, and this variable, they are identical. You can replace them with theta if you want. And so with that being the case, this is obviously 0, and this is 1, their product is 0. So this is 0, this is 1, their product is 0. Again, extremely important. If you don't have x squared, if you wrote x approaching 0, it's not good enough. It has to be changed to x squared, although we all know when x goes to 0, so does x squared, but we have to make sure that it is in this fashion. They all must be identical. All right. We discussed the derivative of trigonometric functions in the beginning. For example, the derivative of sine is cosine, the derivative of cosine is negative sine, tangent gives us secant squared, so on and so forth. Now, we want to prove one of them. By the way, for sine and cosine, for sine, we use the limits that were discussed to prove that. You can see it in my notes if you go back to the lecture. And for cosine, we use sine and those limits again. And the rest of them, we use a technique, more specifically, the quotient rule. So f of x equals tan x. We want to prove the derivative is secant squared. And so we're going to write this as sine x over cosine x. And I'm going to remind you that tangent is sine over cosine or 1 over cotangent. Cotangent is cosine over sine or 1 over tangent. Secant is 1 over cosine. Cosecant is 1 over sine. And these three are known as the reciprocal identities. By the way, if cosecant, for example, is 1 over sine, then sine is also 1 over cosecant. We should know that. So with that being the case, we are going to use the quotient rule f prime g minus g prime f over g squared. So we're going to do this, and I'm going to call this the f function, call this the g function. And so according to this formula, we're going to differentiate this. F prime gives us cosine times g cosine minus g prime. The derivative of cosine is negative sine times sine and over the g squared. Just write this and square it. So in other words, we have f prime g minus g prime f over g squared. Now, obviously, this becomes positive, and many should know that sine squared and cosine squared, they add up to 1. So 1 over cosine squared. Now, 1 over cosine squared. What is 1 over cosine? Secant. Therefore, according to this must be secant squared x. This is one of those Pythagorean identities. I'll discuss those. There are 3 of them in a moment, but I hope everybody remembers them in any order. I'm going to look at another example, y equals secant x, and you can write this as 1 over cosine, and now we can use the quotient rule on 1 over cosine x, and I'm going to write down the top is the f function, the bottom is the g function. In other words, f of x is 1, g of x is cosine. That's what I mean. So we're going to go with that. F prime, the derivative of the top, any number, the answer is 0. So 0 times g or cosine x minus g prime minus the derivative of cosine is negative sine times the top, g prime f 1, and then just over cosine squared. And again, let me write the information at top. So this is f prime g minus g prime f, which gives us, this is 0, this is negative, and negative is positive. So we make it sine x over cosine squared. And as you know, sine x over cosine squared, we can say 1 over cosine times sine over cosine. 1 over cosine is secant x. Sine over cosine is tan x. And that's the proof that the derivative of secant is secant x tan x. I highly recommend you use another one, maybe cotangent x or cosecant x to prove you can use the quotient rule to come up with the answer. All right, I want to differentiate this, and again, we are going to use the quotient rule. So let's write f over g and try to differentiate this. Following the formula here. Again, I'm going to sound like a broken record, but it's important to understand this. I would write formulas that I have learned and I have memorized, and then I would follow the formulas. So I would write that formula, and according to the formula, I have a huge fraction more, and then the top is f prime. Okay, so the derivative of 1 plus sine x is just cosine x. And by the way, I have some of the formulas for you here. So I would write cosine x. F prime. Then times g. Just write it here. Just write the bottom in here. Minus g prime. So the derivative of x is 1 plus the derivative of cosine is negative sine. So it's 1 minus sine x, 1 minus sine x, 1 minus sine x, times f, just times the top. 1 plus sine x, so the top. And then I write whatever I have here in a parenthesis and square it. Whenever you see g squared, just put the same thing and square it. You don't have to square that. Just write it in this fashion, because sometimes they simplify. Now, what happens next, first and foremost, this is a minus b, this is a plus b, and we all remember those are conjugates, and their product is a squared minus b squared. Therefore, just the parentheses here, it's 1 minus sine squared. And this one is cosine x times x. We put the x in front. Cosine x times cosine x is cosine squared, and we don't touch the bottom. So this is x cosine x, this is cosine squared, and this one inside the parentheses. The reason we keep it inside the parentheses is because of the negative sign. Otherwise, if it was a plus, we wouldn't have to. 1 minus sine squared. Now, I did mention sine squared plus cosine squared is 1. Those are considered Pythagorean identities. So let me remind you. Sine squared plus cosine squared equals 1. This is one of them. In trigonometry, we call it a Pythagorean identity. The second one is tan squared plus 1 equals secant squared. And the third one is 1 plus cotangent squared is cosecant squared. And it comes from the original one. If you look at this one and you divide both sides by cosine squared, divide both sides by cosine squared, you get the second line. Tan squared plus 1 equals secant squared if you divide by cosine squared. If you go back to the first line, and this time divided by sine squared, you get 1 plus cotangent squared equals cosecant squared. So the proof of those are extremely simple, but it is important to remember them. Now, when we know sine squared plus cosine squared is 1, that means we obviously know 1 minus sine squared is cosine squared, just as an example. Or we, for example, know that cosine is plus minus the square root of 1 minus sine squared. So it's important to know that we should be able to go from one identity to others. And so obviously cosine squared minus cosine squared, they cancel each other. And the numerator is left with x cosine x. And the denominator, you just write it. You don't have to do anything. You just write the denominator, and that's fine. All right, we're going to continue. And we are going to differentiate this again using the quotient rule. Let me write f over g, meaning the f function is 1 minus secant x and the g function is tan x. So to differentiate this, we are going to have a huge fraction bar again. And at the top, we have f prime first, f prime according to this formula. So this is 0 goes away, minus remains the sign. Secant, the answer is secant x tan x. And because of the negative, minus secant x tan x. And according to this formula, times g is just times tan x. Minus g prime minus the derivative of tan is secant squared. So minus secant squared times f, just write the top next to it, 1 minus secant x. And g squared, simply put tan x to the second power, or tan squared. And I'm going to put an asterisk next to this because I want to emphasize this is the only calculus step, everybody. And we are done with calculus. What is the rest? Everything else is algebraic technique, maybe a trigonometric technique, but this is the end of calculus. And I emphasize this because I want to make sure everybody understands that we really don't have to do a lot with calculus. So the next step is to simplify. So as you can see here, it's negative secant x tan squared. We are going to distribute, we get minus secant squared x. And over here, we get secant cubed. We don't touch the denominator. In the numerator, we can take either the secant out or minus secant. It's up to you, makes no difference. And so let's take the secant x out. So the first one gives us, in brackets, we have minus tan squared minus secant x plus secant squared. And now I remind you that 1 plus tan squared was secant squared. And therefore, I can move this one to the other side, this one to the other side. There are different ways of approaching this. I can say tan squared is secant squared minus 1, or I can say secant squared minus tan squared is 1. And the reason I'm going to go with that one, because I notice secant squared here minus tan squared here, and therefore these two give us 1. And we are done here. Secant x times 1 minus secant x over tan squared x. It's very straightforward, everybody. But I can't emphasize the importance of knowing all the identities, okay? And as you can see, we had only one step of calculus. One step of calculus. All right, we are going to move on. We are going to move on. Y equals cosine x over 1 minus sine x. And we are going to do the same thing, namely use the quotient rule. F over g, meaning f of x is cosine x, g of x is 1 minus sine x. And we're going to go with the quotient rule. And I'm going to remind you that one. It's f prime g minus g prime f over g squared. And therefore, we start with the f function. That is negative sign because we need f prime. We're going to differentiate the top. We get negative sine x. We're going to multiply it by g, meaning we're going to multiply it by the denominator just the way it's given, times 1 minus sine x, minus g prime. So let's see, minus, this one is nothing, gives you 0. Negative remains, sine gives you cosine. So minus negative cosine x. Again, this negative sign just remains, that's why. But the derivative of sine is positive cosine. This negative sign leaves us with that. At the top is f, so times cosine x. And you just write the bottom and square it. So write it in a parentheses and square it. You don't have to change anything. And so the next step is just our algebraic techniques, our trigonometric techniques. So this with the asterisk is the only calculus step, everybody. So let's do that. So this is negative sine x. This is plus sine squared. This is plus cosine squared. So again, negative sine x plus sine squared plus cosine squared. Needless to say, we know that sine squared and cosine squared, they add up to 1. And I'm going to rewrite this. I want to make sure that you see what happens in the numerator. In the numerator, we have 1 minus sine x, everybody, or minus sine x plus 1. In the denominator, we have the same thing to the second power. So the numerator is 1 minus sine x. The denominator is the same thing to the power of 2. So I can get rid of this, change it to 1, and the exponent changes to 1, and the whole thing simplifies into 1 over 1 minus sine x. So it simplifies into 1 over 1 minus sine x. All right, we want to find an equation of a tangent line to the graph of this function. And since we want the tangent line, we need two things. Any line in general, we need two things. What do we need? We need a pair x comma y, x comma y, that is given. What else do we need? We need the slope. We need the slope. And so in order to find the slope, first and foremost, we are going to differentiate, and then we plug in the x coordinate, it becomes the slope of a tangent line. With that being said, first and foremost, let me put a raised dot here, and I'm going to call this the f function, and this is the g function. In other words, f of x is e to the power of x, g of x is cosine x. So we are going to go with the product rule. We're going to go with this one. So f prime, that means itself, the exponential e to the power of x, the answer is itself. E to the power of x, the answer is e to the power of x. So e to the power of x times cosine x times g. Plus g prime. The derivative of cosine is negative sine. So plus negative sine x times f e to the power of x. So let's write at top of it clearly as to what we have, and that is f prime g plus g prime f. It's important to know the reason it becomes negative is because the derivative of cosine is negative sine. So let's factor the e to the power of x out. It makes it easier to see. And then m, the slope. we plug in 0. So if we plug in 0, we get 1. Why is that? Let's quickly show you. So y prime of 0 is e to the power of 0 times cosine of 0 minus sine of 0. And as you know, this is 1, this is 1, this is 0, and so the answer is 1. Now, normally we would use y minus y1 equals m times x minus x of 1. However, what is given is the y-intercept, 0b, that means b is equal to 1. M happen to be 1 also. They are not always the same, obviously. So using y equals mx plus b, I can write y equals x plus 1. Y equals x plus 1. Here's the next question. We want to find the points for which the tangent lines are horizontal. So there are two things we want to pay attention to. The concept of tangent lines and then horizontal. So first, the tangent lines, that means differentiate. Differentiate. So f prime of x, so this means differentiate. F prime of x is 3x squared minus 6x. And then horizontal. As you know, the slope for any horizontal line is 0. Let's just write it. Horizontal lines, the slope we know is to be 0. So therefore, we must set it equal to 0. And this is a simple algebraic step. Again, the only calculus step, everybody, was this one. We're done with calculus. Everything else we do is algebra. So first we take the 3x out. So 3x times x minus 2 equal to 0 makes it either x is 0 or x is 2. Now, we must write them in pairs unless they just want just the x coordinates. Normally, when they say points, they want them in pairs, meaning when x is 0, you plug in clearly becomes a 5. When x is 2, 2 cubed is 8 minus 3 times 2 squared, which makes it minus 3 times 4 is minus 12, plus 5, and that makes it positive 1. So you plug in 0, you get 5 into the original function. You plug in 2 into the original function, you get 1. Therefore, this function has tangent lines that are horizontal at the pair 0, 5 and at the pair 2, 1. So I hope everybody's okay with this.